Go for it, Bob. It's all yours.
Right. Yeah. Okay. Well, what I'm going to do is I talk a bit about me, because it's supposed to, this whole thing's supposed to be about engineering as a career and the wonderfulness of it, the excitement of it. So I'll do that a bit, and then I've got a sort of slideshow really, and then a slightly more technical bit about solar energy, standalone solar energy systems, and so on. Okay. Well, I was born end of the Second World War in Sheffield, nice engineering place. Fascinated from an early age about making things, and nothing pleased me more than some Meccano or a battery and a few bulbs to play with. And crystal sets, that was my first proper venture into electronics. My first crystal set had a coil wound on a jam jar and a pair of XREF headphones from the leftover from the war, and the diode in it. For those of you who know about crystal sets, they need a tuned circuit and a diode to convert the RF to AF audio frequencies, and that was a bit of coal and a piece of fuse wire. So and you tuned it by stretching and squeezing the coil on the jam jar. And yeah, so that was my first electronics achievement. I suppose I had an engineer as a dad, and he worked in the steel industry, more of a mechanical engineer person, but there's not much money around at that stage, so there was very much can-do thing about, if you can't afford it, you can make it. And fortunately then in the electronics world, you could. I mean, it was so much cheaper to make something than to buy it. And that's not the case now, of course, very often. So I kind of grew up with that idea that, you know, if you fancy having something, you make it. I think the other thing that influenced me was that era. That was kind of early 50s. TV was really just getting going, and that really did fascinate me, and I really wanted to know how it worked exactly. And I've got one of the first books on colour television that dates back to 1950. So I was only about 11 probably back when I got that. So I really was gripped by television, and I suppose that got me into electronics really. I did go to a youth group though, which stopped me from becoming a complete nerd, and broadened my outlook on the world and other things, and that was great, camping and everything else. And then in 1964 I went to Southampton Uni to study electronic engineering. What else? And I remember even the first week there, we had this interesting talk by the Dean of Engineering about what it was to be an engineer. And you know, part of it was the usual things about the responsibility of engineers for people's safety and so on, well-being, and the whole thing about having to balance quality and cost and so on. But what he did say was that, as well as all those things, engineering was actually very influential, because you could choose what you were going to put your talents into, what job you actually chose to do. So if you had any beliefs, you know, you didn't just take the first job that came along. You went and put your talents into something that you really believed in. And the other thing is that technically competent people were very important in other discussions, philosophical and future things, and climate now and so on. And to have people who had a really good technical grasp of real world things and real world solutions was very important in that debate, rather than kind of it carrying on at a level which wasn't really grounded in things that were practical and possible. So I remember that from the first week at uni, and it just came back to me, and I was thinking about this. But I mean, the other thing is, it was great fun, and I'm just going to try and start this slideshow, which is a Host disabled screen sharing. So would you like to let me share screen, Debs? Yeah, that little green box at the bottom. And next to it, there's a little arrow, up arrow. If you click on that, you can let other people share their screens. Can you see it? Little square share screen box. No? Yeah, I can't hear you. You're muted.
That's true. I was saying, yeah, I've clicked on it. You should be good to go.
Will it work now?
Should do.
Yes. 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 Okay. Okay. I think it's yes. Except I'm now not at the right place in this. But hang on. Yeah. So I was just saying that it was actually great fun. Hang on. Right. There's that's it. I've got my mobile running. That's why there's my name up on another screen because it's as a sort of monitor, because there's a long delay. We're on a really slow connection, so the upload speed is really slow. So I need to know whether I'm talking about the same slide that you're watching or not. Yeah. So university was great fun. Very hard work. Those days, the engineering course like that was solid lectures and tutorials. I think there was a 2-hour slot on a Wednesday when you didn't have to do formal work. The rest of the time, it was nose to grindstone. And I know a lot of engineering courses aren't quite like that now. But anyway, it was hard work, but we did some great fun things as well. This is the bus that we took across Europe. Some fun and games with that, trying to take it over the Alps under these snow sheds and things like that. And yeah, and then I decided to do a PhD, and I did a PhD on adaptive control systems. And in this case, it was applied to artificial limbs, particularly hands, which are really complex. And most people who've lost one hand just prefer to manage with something simple. But when people have lost both, the ability to manipulate things becomes quite difficult. And so there's a lot of work's gone on. This was back in, when was it? Late 60s. And a lot of work's gone on since, and there's some really remarkable devices around now. But this was an early venture into that. It's controlled by tiny signals from remnants of muscles in your forearm, if you've got one, or other nearby muscles. And then the novel thing about it was it could adapt the type of grip. So most of my work's been concerned with tiny little signals. I mean, I've just put this up because Bob, the other Bob, was talking about this end. If you put watts on the end of all these things, he was in this region, gigawatts, megawatts, gigawatts. Terawatts we only really hear about when you're talking about the whole consumption of countries and things, probably, but megawatts, big wind turbines, and then kilowatts, lots of, and big solar farms, kilowatts, you all know, some domestic appliances, and down to like 1 watt is probably a torch or something these days, and going down that scale to milliwatts, usually jump in facts of 1,000. Milliwatts, things get more electronic-y and interesting. Wi-Fi transmissions are in that sort of headphones, power to headphones, audio power, and down another 1,000 times to microwatts. and that's the output of a microphone when you're not shouting into it. Just to, interesting. Compare that. That's Moonlight's about 500 microwatts, something like that, which makes you full the eyes because it can in 500 microwatts, but it also can cope with bright sunlight, which is about a kilowatt per square meter, and compared to microwatts, about 500 microwatts per square meter, which is a huge 10 to the 6 about difference. Then down to nanowatts, we're in, that's about the signal level you get from a TV antenna. You know, if you've got a TV antenna on your roof. And it's about the level we're allowed to transmit in the FM band without a license. We're down in the nanowatt region. And picowatts is interesting. That's 10 to the minus 12 of a watt, rather a lot of noughts. And that's about the power density you get, picowatt per square meter from satellites, from say satellite TV signal or something like that. So I thought that was quite interesting. And as I say, the other Bob was working up the top end here, and I spent most of my life working at this low end. But let's move on. And physically small too, massively heavy generators and things at the megawatt scale. And this sort of stuff, this is quite an old one, so it's actually big by modern standards. But these integrated circuits, I don't know if you can see the detail there. And with the modern ones, the later ones, even, you know, you really do need a microscope to see what's going on sometimes. So a big range of things. After I'd done my PhD, I taught the electronic engineering at Southampton actually for about 5 years, something like that. Then moved to CAT, Centre for Alternative Technology in Wales, after I'd done my stint as a university lecturer. That was really being dropped in the deep end. The idea was to demonstrate ways of using technology which were kinder to the environment, basically. And the thing that got me interested in this whole thing really was back in the early 60s, the Limits to Growth and Smalley's beautiful books. And so after I'd done 5 years of teaching electronic engineering, which I quite enjoyed and learnt a lot, I then decided to go and work at CAT at about a tenth of the salary. But it was a worthwhile move, and I really learnt a lot. We actually had the place running entirely on, well, not entirely, but from an electricity point of view, on renewable energy. And that was only achieved then by a lot of very careful minimizing of power consumption. I think we ran the whole place on about 2 kilowatts for the first probably 10 years. We had a lot of visitors. 50,000 in a year was not uncommon. And because there was an increasing interest in this whole field. But quite a few of the visitors said, well, this is all very well if you just want to run a caravan on it, but or something like that, but it's never going to make any impact nationally. And so I got together a group of people I'd met who were working in different fields of renewable energy, and we produced this little report, which was a admittedly fairly optimistic look at how you could move from the national energy predictions, which were looking crazy already. I mean, this was the predicted growth in energy consumption from 75 to 2025, and Department of Energy were predicting a range of things from this to that, but the target was very much up to the top end. You know, so they were really thinking of huge growth in energy consumption, and the scenario that we came up with was suggesting something more like that. And I think that's a lot nearer to what's actually happened than they're very optimistic. But all this business about predicting anything, as you know, is dangerous. This is IBM's chairman saying there was a world market for just about 5 computers. He thought this was in the 1950s. So I'll not bother with that. And I had lots of fun things to do at CAT as well. This is the prototype of a controller for the Cliff Railway. I don't know if any of you have been to CAT, to CAT. It's got a water-powered Cliff Railway, and controlling that speed and everything else was not easy because it's got massive water tanks underneath it, and the water sloshes in it and gives it some very interesting dynamics. So this was the prototype of the controller, and we never ran that particular one with people in it. But the final thing was a bit neater looking, but that just was to prove the point that it was going to work okay. Right, let me think, where are we at? Yeah, the other thing that came out of that report that I just showed you was meetings with, because we sent them all over the place, sent them to a lot of politicians and so on. And Sir Martin Ryle put his name to the front of it as well and said it was a good thing. So we got quite a bit of exposure with it, and now was invited to meetings with Energy Technology Support Unit at Harwell and with the Electricity Council, and quite a lot of IE talks. And there was a beginning of interest in the architectural profession at that point. It's about 1976 or 7 or something like that. The other things at CAT was courses. We started running courses on a wide range of topics, but as you probably know now, that some of those have grown into fully accredited MSc courses on renewable energy, aspects of renewable energy. And also we had an electronics workshop making gadgets originally, which we needed, but then other people asked us if we could make things for them and so on. And that's how Dulles was born. It was initially called Dulles Engineering, and it's a company now that I'm not sure exactly how many employees it has, but it's well over, I should think, well over 40. And it's been very active in renewable energy of all sizes, hydro and solar and wind. So it was around then I got really interested in woodcraft folk. I did a couple of sessions on various techie things with the local group, and I was really caught by it and was excited by all these interesting young people and inspiring very often. And I wondered whether there was much enthusiasm about engineering in those days. Anyway, over the years, I've tried to introduce an interest in problem solving and technical things and trying to understand and be interested in how things worked and everything else. And we do these regular, what we call them a scrapyard challenge evenings, where they have to, in several teams, try and solve some problem. And it can be anything from getting dried peas from one end of the other end of the room to the other and into a small receptacle, to making a egg timer out of whatever's around, and bits of electronics. This is one of those twisty wire things, but they actually, it rings a bell if you touch the wire with a loop. But this one actually has a thing that detects when you have and remembers and tells you. And they put it all together themselves, and they get really quite excited about about them. And another one I've done a number of times is actually making a loudspeaker out of a bit of paper and a bit of wire, and you get some music out of just this piece of paper and a bit of wire and stuff. So all those kind of things are good fun. This is an interesting one. What's the tallest thing you can build out of a copy of the Evening Standard? This was, that's the tallest yet, I think. Bit of structures, and another structures one. This is barbecue sticks and what they call those squishy things, you know, those for joints. Good fun. What?
Marshmallows.
Marshmallows, that's it, yes. I'm getting old. Yeah, and then when we go places, I always usually try and persuade them to take a slight interest in some techie things if we find one. And this is one of the big hydro plants in Wales, and this is just a turbine. You can play with a few megawatts of turbine, and great thing to sit on and mess around with. And camps then, of course, we started wanting a bit of electricity at camps rather than just running torches down. This was a camp which was very near the coast. It was on a sort of high spot. The sea is just off to the right of that picture. So it was pretty windy, and there's a little wind turbine that provided most of our electricity for that camp, including being able to show a film. But that's unusual because most places you choose to camp are not windy. So we've almost always used PVs to provide power for camps rather than wind, because most nice campsites are not very windy. But in fact, the power density of wind is similar to that of solar. Solar energy peaks at about 1 kilowatt per square meter, and wind is 12 meters a second is kilowatt, about the same kilowatt square meter ish. And the problem is a kilowatt per square meter of sunshine is quite pleasant, where 12 meters a second wind it probably isn't. So PVs it is for most camp power things. Where do we go next? Oh yes, and then come from the solar trailer era. So this was probably the first one, which was the Leicester woodcraft folk were interested in building one, and that's what happened. That's it. About 500 watts of peak of PVs and batteries, an inverter, and it's been used at many camps. And here's some of the woodcraft folk people building it, and that's the control panel for it. Hang on, are you seeing that yet? Yeah. Then there was the Edinburgh one. This was designed by a group of Edinburgh Edinburgh venturers, in fact, who came down to Wales and had a whole long weekend trying to work out what they wanted. They had very high ideas. It had to be like a mobile cinema and do absolutely everything: mobile smoothie making, hair cooling, hair curling, hot water, everything. So this was a bit of a much bigger and heavier thing and more complicated. It had a solar water heating panel that hinged out the side, and a system for making selling food through a hatch. And it now lives at Biblins, and this is the inside after it had been tidied up a bit. This is the inverter that converts 12 volts in this case up to mains voltage. It's the controller. We'll come back to that in a minute. That's Ron Brown, whose inspiration the Edinburgh one was, and he was chair of Craft Folk for a while. And then I got involved again with sort of young people in powering small remote premises. And this was first water turbine I ever put in, which was a 2 kilowatt about, up the hill quite near us really, powering a remote house up there. And sort of old Pelton turbine. Got free. It was found dumped behind the local garage. The costs were the pipe and the cable. And this wonderful place that we in North Wales that we often go to, called Cae Mabon. We put it's got lots of copies of ancient British buildings, roundhouse and various other things, and we put solar heating, solar lighting in all those. This is the work going on that. This is the final effect, some nice gentle lighting to try and go with the era of some of the buildings. This this is in the roundhouse, and we had to hide the panel. It's in woodlands, so there was only really one place we could have a decent shadow shading free spot. The panels are up on top of that building there. There's the control box for it. That's a gang of young people enjoying the place. Then we've got another place up in North Wales, which is right by the sea on a little estuary called the Shed. I'm not going to the history, but it's quite interesting when you've got more time. We got more time. We put in there, yeah, it's a great little spot, and it makes it quite usable to go for you can get in the estuary if you're brave, and that's our venturers. In fact, earlier this year, crammed in there. A lot of the camps and things we've done with a bit of UV fun, because it doesn't use much power really, and it's just another way of saying, well, what's going on when you do this, and why does it work? And then there's the big camps. Global Village was 2006, and about knocking on for 5,000 people there. And of course we couldn't power all that, but we did power a couple of villages within the camp, and that was the first year that we did a serious camp TV system, and that was another thing. That was our our test card for the camp, and that's taken in one of the town marquees, showing the nightly news. I don't know, those of you who know Woodcraft camps in recent years will know that the big camps, it's become a tradition to have a nightly news broadcast, which is made up mostly of things which young people have videoed during the day, picking up all sorts of things that are happening around the site, and that all gets cobbled together into a maybe half an hour or more news broadcast. And in this case, we were broadcasting it around the site, using about 10 milliwatts of transmitter power in the 2.4 gig band, same band as Wi-Fi commonly uses, but this is actually a FM analog system, about the same kind of modulation type as the early satellites used. And yeah, there was some good humorous stuff and so on. That's me making last minute touches to the receive antennas, which were horn antennas cobbled together out of a couple of co-op tins of potatoes, which happened to be the right size and happened to solder nicely. So, and the transmitter is most of my things that have to go outside for a camp go in food boxes like this, because they're nice and cheap and they keep the water out. And that's one of the receive antennas in a big marquee. that's a solar powered repeater, because on the site we used for one of the camps, it's got a real, this wasn't Co-Camp, this was Co-Camp, not Global Village. It got a big hill in the middle, and so to get the signal, tiny signal over the hill, we had a repeater there. And lots of other things on Global Village going on, which were very educational from a technical standpoint. There was a house that you could experiment with changing design in various ways and looking at its energy consumption, see what effect different things would have. We built a sauna. This is lots of educational stuff about insulation, different types, pros and cons of different types of insulation. And you can see that was a really good project because it involved a lot of people. And one of the things about technical projects, I think practical projects where they actually achieve something are great because people actually remember stuff then. But it's really hard to come up with good things that involve a lot of people. And so that was a good one because there's different skills, lots of different skills, and that's a lot of people crammed into it. It's all a bit steamed up and it's working there, wood fired, yeah. And we also built some showers on that camp. They actually built solar showers. These were supposed to be cubicles for the showers. They were cutting pipes and doing everything, and they actually made the solar collectors. They were clip fin type collectors where you have an aluminium fin that's shaped so it snap fits onto a copper pipe, and you fill the thing with a heat conductive paste, get good efficiency. And some of the younger kids were building small model ones to try it out, but that was the final thing. That was as far as they got. There were supposed to be 10 collectors, and I actually managed to make 5. But different towns within the camp each built one, so they felt some ownership of it, and that's the shower tent. That's it being used at another camp later. That's some bathing beauties. And then we got home from that lot, and our venture, we heard about these co-op and various grants, and said to our ventures, what do you want to do? We could do a project that costs money. What would you like to do? And they came up with the idea of building a solar cinema. And so away we went and we did it. Struggled to find a suitable tent because most tents now are white and not very good for keeping the light out. So army tents. And in fact, there were 2 built. Again, Leicester built one and used the same tent, so we can put both of them together and seat about 70 people. So that's just a blurry view of inside the tent. Okay, a bit more technical stuff. Now you're getting serious about using a bit more solar power and it being kind of more important if it doesn't work. You know, if you're showing a film and it runs out halfway through, people get pretty fed up. And if you're trying to power a big camp like the Venture Camp in last year, you know, you really don't want it to fail. You've got to do the sums and try and get it right. This is an indication of how much solar energy we get throughout the year. It's southern England, but it doesn't vary very much in the UK, plus and minus maybe 10% over the most of the UK. Most of our camps occur between like April, May and September really, and so most of the time you can say that we've got more than 3 kilowatt hours a day, that line through there, and that's the amount of light energy falling on the ground per square meter. This just splits it into diffuse and direct radiation. That doesn't matter for the moment because PVs respond pretty well the same to both. But the question is the variability of that. These are a bit deceptive because they're averaged over a month. And so if you look at the daily things, you get something more like this. And this is basically saying, well, the extremes of that smudge, the extremes of it, are the minimum and maximum days throughout the year. And this is what's called capacity factor. So that's really the fraction of the energy that a system would produce if it was brilliantly sunny all day and night. Yeah, so that would be your kind of maximum output you could refer the thing to. So about 0.12 corresponds to that 3 kilowatt hours a day thing, and it goes across here somewhere. And so you can see if you take that figure, it's very rare for the minimum daily thing to drop below that. And if it does, it only does it maybe for a day or two. Yeah. So mostly I've taken that as a rule of thumb that you can count on an average of 3 kilowatt hours of input a day. You can, of course, model this totally. There's some perfectly good modeling programs which allow you to simulate a PV system and so on. But there's so much uncertainty in what you input to it, like what the weather's going to be like, what the consumption is going to be like, and so on, that I think for this kind of application, it's probably not worth doing. But this sort of long-term data gives you a good idea. The actual PV modules, photovoltaic modules, have come down a lot in price, as you probably all know. They've got interesting characteristics. I'm not sure how many of you are electrically inclined, but I'll just explain it briefly. They're completely the opposite to a battery, in that a battery is a constant voltage thing. So, say a car battery, nominally 12 volts, and even if you take quite a bit of current from it, it's still 12 volts roughly. Whereas a photovoltaic module is a constant current thing. So, and the current it produces, if you look at this solid line here, this is current up the side, up the left-hand side, and the current it produces is independent of the voltage across it. So if you put a short circuit across it, it still gives you the same current, and it doesn't blow up or anything. Doesn't even get hot. So, but if you don't draw any current from it at all, it has a kind of maximum voltage that the voltage rises to. Yeah? Now the power you get from it is volts times amps. So if you look at the voltage across the photovoltaic module, when you're right up here, you're not getting any power out. You're getting quite a lot of volts, but no current, no amps. And as you reduce the voltage a bit, the power goes up to a peak there. And then as you come down, you've got a constant current and less power at the lower voltage. So ideally, you want to work with the panels matched to the battery voltage so that you're working on that, what's called the peak power point. And the problem is that this line is drawn for bright sunshine, and as the light level drops, the current drops fairly obviously, but also this maximum voltage drops. And as the temperature of the panel varies as well, this voltage varies, and the hotter the panel gets, this voltage reduces. So it's quite difficult to match exactly the battery voltage to the panel. And so more recently, people have been using what's called a maximum power point tracker, which is a box of electronics that converts power at one voltage to power at a different voltage. So maybe your battery is at 12 volts, say it's recently been discharged, whereas your panel's best voltage is at 17 or 18 volts. And so it absorbs power from the battery at that voltage and gives it out to the battery absorbs power from the PV module at that voltage, gives it out to the battery at a lower voltage, so less voltage but more current. Yeah. So we've got to try and get all that right, and I'll show you. Hang on. Yeah, I'll just mention that while we're looking at it. This is Google Earth, and it's wonderful for planning camps from a techie point of view. You can zoom in on it. That was a camp we did near Lake Bala. This is Lake Bala in North Wales. There's the field we had, and you can see the water point we had was here, and you can actually, it's got a ruler in the system. You can measure how much pipe you need, where we were going to camp, and how much cable we were going to need, and so on. And the other wonderful thing about it is it'll do solar shading, so you can tell it the day of the year, and if it's a clear day, and you can pick the time of day, and it'll show you where all the shadows are from nearby hills or whatever. So that's really great for being able to remotely look at a site in detail and try and try and design it. Let me go to this paper. Hang on. Just come out of that. Right. So with a bit of luck, yeah, we've got. Right. So how much PV do we need? Well, I'll just take the solar cinema as an example. So what we do, we need to work out the daily energy consumption. So so can you see that? Is that, yeah? I'm not getting any response back, but never mind, I'll carry on. So what have you got in the solar cinema? You've got a projector.
Yes, we can see it, Bob.
We can see it, Bob. Yeah.
Good, yeah. You got a projector, and its power consumption, the one we typically use, is 250 watts. We've got a player. We usually use a DVD, a Blu-ray player, because it on a big screen, it's nice to have a Blu-ray thing. That only takes 15 watts. We've got sound system. Again, that's a high efficiency amplifier, 50 watts a channel, so 100 watts total audio possibility. But how much power does it take? Well, it averages about 15 watts. Now, people are a bit surprised by that sometimes. It takes peaks. When you really turn it up good and loud, it takes peaks which are close to its roundabout its rated power output, i.e. 100 watts. But with most music, and certainly filmed soundtracks, there's a lot of silence and so on. So although it peaks up to maybe 100 watts, its average consumption is only about 15. And then you've got some lights, and so they're not on a lot there, but they are, you know, there's people in there during the day sorting things out and so on. And so I guessed about 10 watts or so average. So if we add that lot up, it's about it's the best part of 300 watts. Yeah. So, and how long are we going to have that for? So a film is 1.5 hours, and we typically on these camps where we use it, you'd be showing 3 films a day. So this is times 1.5 hours is about 450 watts. Let's say half a kilowatt hour per film. Yeah. So it's about 1.5 kilowatt hours per day. Okay. Now the thing was said earlier about 3 kilowatt hours of sunshine per square meter per day. means that to find out how much your PV panel will produce, you have to take its rated power and assume that it produces its rated power for 3 hours a day. So this would, in theory, only need about half a kilowatt of PVs to provide 1.5 kilowatt hours a day. So we tend to oversize that, and you need, as we said when we looked at that variability thing, you need a few days storage. So we usually go for 2 or 3 days storage and try to keep erring on the safe side, because you want people to come experience a camp with lots of renewable energy, and you want it to work. So you want a high reliability of on the thing if you can possibly get it. The other big thing is about design for this is safety, and this electrical system, like we did at Venture Camp. There's the physical stuff, electrical, in other words, electric shock, and there's batteries. Physical stuff, it's mainly kind of trip hazards, things like that. We protect from that by trying to keep cables above head height or well protected in some way. We've got these rubber things which are walkover rubber cable covers, and fencing off areas where there's a lot of cables, and round where the solar collectors are. So that's fairly straightforward. Electrical safety, avoiding electric shock. Well, camps are difficult for that. There's the big problem of wet, that you can have unexpected deep mud where you thought everything was nice and dry. So wet ground is difficult. So we try and keep all electrical equipment and connections off the ground. There's the problem of long leads, long cables, which often mean lots of kind of chained together extension cables very often, and that's generally frowned on. The main reason, you obviously get volt drop and things like that, but you can deal with that and get the loading right. But the thing that people worry about with long extension cables is that the more connections you have, the more chance there is that the earth protective conductor will not be good and will not provide electric shock protection. And the way around that is to provide multiple earths. So, and this is particularly important where people might be using equipment which has got an protective earth cable, such as PA equipment. If you've got somewhere with PA stuff or a band or something like that, they're all holding often metal microphones which are connected to the earth protective conductor. And if somebody trips over a connection and yanks the earth wire out, then you could make the whole thing live and cause a hazard. So multiple earth things, and particularly where you've got those kind of things going on, and always an RCCB, which is a residual current circuit breaker, and that basically measures the current going down the live conductor, coming back down the other one, and those two should be exactly the same. If they're not, it detects a difference of about 30 milliamps and disconnects the supply within a few thousandths of a second. And where I'm slightly worried, I always use 2 of those. You can put them actually in series, so if one fails, the other will still do the job. So those kind of things. And you've got to be particularly careful on camps because people are often in barefoot, and sometimes if you tell them it's solar powered, people make the wrong assumption. They think solar powered, oh, it's only 12 volts or something, or it's not very powerful and it's not dangerous. And the other thing is to turn it all off at night, which is what I usually do, because you can get nasty winds can blow up in the night, tents can fall over, and your carefully arranged wiring can be seriously damaged. So power it off at night is my general rule. Batteries, lead acid batteries are the ones which are the most economic to use still, although there are lots of much more tempting ones around. They got acid in, so that's a hazard. If you short circuit them, they draw enormous amounts of current and can melt your spanner before your very eyes. They can cause fire, and they give off hydrogen. So they're basically quite hazardous things, so they need to be kept out of harm's way, where people don't fiddle with them. The hydrogen risk is very low. I think if in a camp it's too much ventilation if they're in a tent. But the other things are certainly worth worrying about and protecting against. Okay, so that's enough of that. And I've really almost had my hour. We didn't start a bit late. Is it okay to just carry on for a few more minutes? Somebody? Debs?
Yep, by all means, carry on.
You might have had enough by now, yeah. Okay. Right. Right, I need to get back to here, and sorry, I'm lost. You know how you can get lost sometimes.
While Bob's sorting that out, I'll tell you a little story about him. He shows our Venturers films in his barn, and he can set up this clever thing with 2 projectors and show a 3D film. And the first time he did that with the Venturers, at the beginning he explained to them how it worked. And then at the end, they actually asked him to explain again because they were really interested in how it worked. I was very impressed.
Good. Right, are we there? Yes, we are, I think. Oh, sorry. No, don't do that.
It's the other Bob here. I'll say something while Bob's looking for that.
Yeah.
Yeah, I did some work for the Electrical Safety Council on testing of RCDs and RCCBs.
Oh, right, good. Yeah.
In a like a camping environment, an outdoor environment.
Yeah.
So from a safety point of view, it's quite important to operate the test button and make sure that it actually does work if you actually get a fault, you know, if there's a difference.
Yeah.
In neutral.
Absolutely, they do it every day on both. If you got 2 of them in series as well. Yeah, another thing we've done is to try and involve the young people in the whole safety thing as well, by having a small group of what we call power rangers, and they are trained up at the beginning of the camp to look for hazardous things, like, because even if you set everything up nicely at the beginning, you know, people come along with old toasters, you know, and stick them in the wet grass, and you know, it's crazy things sometimes. So we trained up a few young people to go around and sort of keep an eye on the system as well, and it involves them in the general thinking about that sort of thing. Yeah, this was what venture camp was probably the first one where we used photovoltaics to power the main central area. This is one of the projects was making some of these LED displays, and it just again involves people in a bit of the technology and some of the, come on, this is very laggy. I'm on the next slide, that's it. And yeah, this was a Woodcraft folk symbol. Yeah, that's the back of it, but that's the finished thing, and that's made it coming up. I'm watching it on my mobile, that's it. Yeah, so it's been used at a lot of camps since. And at one of the camps, we actually got the different towns to make their own symbol of the town's name in LEDs. Then this is preparing for CoCamp. We were going to have a radio station. We had a radio station back at Lowell Village in 2006, but we paid for a special license for that, so we could transmit with about I can't remember now, it was a few watts we were allowed on the FM band, and it cost quite a lot of money, some thousands of pounds by the time we finished, just for the licensing. And the idea was to try using these little FM transmitters, which are license free, which are intended for allowing you to listen to music over on, say, a car radio, or to transfer it around the house. They're limited to, the power is limited to 54 nanowatts, which is really pretty tiny. And at first we thought, well, I'm not sure we can get any sensible range out of that at all. But if you dangle the cables around a bit and you use some good receivers with a good, very good sensitivity and selectivity, then you can get maybe up to 200 meters out of it. So that's what we've used on several camps. This is our ventures testing out this thing, tall thing, white thing, is a piece of old drain pipe, plastic drain pipe, with one of these little transmitters, sticky tape to the middle, and the cables draped over the top there. And they were walking down the main street in Machynlleth testing out the range of this. And so we've used that on a number of camps. This is a CoCamp, again, TV. This involved quite a lot of people. There's a really good media centre producing a daily newspaper, which was pretty exhausting for them, and nightly news broadcast, and running a radio station all day. And this is the radio side of it here, and this is the TV side of it here, and this is the video mixer, and there we go, and the rest of the stuff. Keep an eye on what's happening. And this was the first time we actually did the news with live presenters. This is it during the broadcast. People are all getting a bit tense. This is the sound crew. This is CoCamp News. 2 live presenters there doing the biz, rather than just having a pre-recorded thing. The radios we've used at various other camps. There's a single transmitter at this camp in Scotland. Again, kids really getting into it and understanding it quite well. This is a physics teacher from the local school who was really turned on by this and wanted to go away and do it again. We're powering the whole radio station off this little PV module and so on, so tiny amounts of power. Then VCamp 2019 wanted a radio again, this was the layout of the camp. And some of you will know Biblins, some won't. It's a lovely campsite by the River Wye, and it's on a serious bend in the river, which is very nice, except if you're trying to transmit a radio signal, because the central area where we wanted the radio station to be was around here, and we needed to transmit it all the way along there and around here. And the problem is the land here is quite high up, so it completely obscures the line of sight from here to there. So there's no way that 54 nanowatts is going to get round that corner. And so we did a two-stage thing with a UHF link using another license-free frequency, and managed to get the persuade signal to go around and then have a repeater at normal VHF FM frequencies there. So that's in our barn, and this is me fiddling about with the antennas to get that working. These are repurposed old TV areas and checking out the behaviour of it. And yeah, I'll skip some. Our ventures then made half a dozen of these radios, which have got a digital front end, which is has very good sensitivity and selectivity. Selectivity means it can ignore much more powerful radio stations, which are frequencies very close to the one you're tuned to, which is important. So yeah, that's inside. It's got some big batteries, got the speakers, and this now ridiculously small little board that does everything. Most of it's in this DSP chip, which digital signal processing chip. So radios have changed quite a lot. There's the radio tent. That green and red thing is the local FM aerial, which is serving this central area. In that food box on top of the pole is a UHF antenna running at about 860 megs, which was sending the signal off to other FM transmitters around the site. This is the actual radio station with Joel there and a continuous group of people sat watching, and Jack Walker having a discussion about something. And yeah, that was a really popular part of the camp. For the camp, VCamp 2019, we built a new set of PVs because we're having to power the whole camp off this. There's no other electricity available on the site. We've accumulated all these PVs down the front here over several years. So there's about 2.2 kilowatts worth there. And then we built a new 2 kilowatt system. This is the storage batteries for the new 2 kilowatt system, about 10 kilowatt hours worth there. And that's a sine wave inverter, which up to about 5 kilowatts peak. But it's interesting in that it's got the center tapped output. So if you ground the center tap of the output, it means that your maximum voltage to earth is only half the normal mains voltage. So it's 110 or 115, which is the sort of approach that's used on building sites to improve the safety. That's a controller, and hang on, that's the, yeah, and that's the main marquee with all its lighting and kilowatts worth of lighting and 2 kilowatt PA system. But again, even with a PA system like that producing loud music, the power it actually consumes on average is nothing like the power that the trumpets on the nameplate. People like to make them sound really powerful, which they are for split seconds, but the average is much, much lower than you might expect. So these are kind of thing it allows. There's a solar cinema down the far end of the main street. That's inside the cinema. And of course, the inevitable phone charging. So a look around Biblins quickly, the various buildings which have mostly got bits of solar. The warden's cabin, quite a few bits were put in many years ago, and that's the diesel generator that was also put in, that gobbles enormous amounts of diesel even when you've not really got any load on it, and that's now been removed. So the site is entirely renewable energy based from an electricity point of view. It uses a lot of gas for hot water and cooking, and in fact there's a project underway to look at how we could in future completely power the place renewably, and it's a lovely opportunity to do that. But as I say, most of the energy consumption of the site is gas, not electricity. So the electricity bit is kind of relatively easy, but if we're going to tackle the gas consumption, we need, much bigger solar collectors or whatever. And it's all still a bit up in the air as to how that might be done. And so that might become part of this whole project we're involved with at the moment. That's just a pretty lights at the annual gathering, and I'll stop there. Okay. Right. Hope that wasn't too long.
Thank you,
Any
Bob.
questions?
For me, it was a nice trip down memory lane, seeing some pretty
Memory
photos.
lane, yeah, I'm sure it was. Yeah, not everybody's sort of witnessed the sort of thing. I'm meant to say as part of that. I mean, somebody's bound to ask about the economics of this. When we do it at camps, we're not doing it for economic reasons, because if you do the sums, it just doesn't add up really. It sort of can partially. I mean, the thing is, for something like Venture Camp, we'd have had to, at Biblins, we'd have probably hired a quite expensive diesel generator. And so we saved probably hundreds of pounds on that, but we actually spent more than that on bits and pieces and so on. But we've ended up with capital equipment, which will last quite a long time. So it's not too bad a deal financially. But the main thing is an educational one, really, I think, and letting people realise they can have a good time on relatively small amounts of power and sustainably produced stuff as well.
I think my experience of the camps is it's the first time that young people often think about the electricity needs of their choices, and particularly venture camps in the past where people have gone, oh, if I use the electricity to make my toasted sandwich, then I don't have my electricity to do something else. And that I think is always positive. But the thing I want to share, which has got absolutely nothing to do with what Bob's talking about, is the first time I met Bob, he was up a ladder with a roll of gaffer tape trying to correct the broadcast transmitters because they were suffering in the sunshine and melting. And that memory will always stick with me forever. So thank you, Bob. I don't know if you remember, but I do remember. Does anybody have any questions for Bob?
No, it's fine from the other Bob. I remember I've seen the PV trailer at a venture camp years ago, and I can see it's progressed a long way since then. It's good.
Yeah, yeah. The Scottish one was really well used because they managed to raise money to get a person and to take it round schools and do demos and education and things like that. So it was really quite heavily used for that, not just for the occasional camp.
Matthew, were you part of that team that designed that one?
I wasn't part of the team that designed it, but I was. I did a few of the workshops at schools that it was used for. I was a bit young to design it then.
Mm-hmm.
Could you do hydro at Biblins, Bob?
You could. The licensing would be difficult on a river like that, and because there's very little change in height. The power you can get is the height fall times the flow rate, basically. So there's plenty of flow rate, but there's very little height change. So historically, somebody would have dug a long leat from back upstream to bring the water down parallel to the river, but higher up, and then let it drop back into the river. There are turbines that you can, like a wind turbine, that you can just turn upside down and dunk in the water, and the water turns it as it goes past. But unfortunately, logs and all sorts of other things go past, and they're not very easy to make durable.
I remember the name of the screw one that has a horizontal shaft.
Yeah, that's right. Archimedes screw type thing.
Yeah. You see that?
Yeah. So it's very tempting. See, when you see all that water going past, you think, gosh, there must be a lot of energy in that, but it's really quite hard to extract it. Most hydro turbines hydro systems that of a small size that people make are really high head ones, where the water falls a long way and there's not a very large water volume. So you can get the power, and then you only need small pipe, and you get high rotational speeds, which is easy to connect to a generator. Whereas if you've got a very large flow and very little fall in water, then you end up with something that turns very slowly and has to be physically very large to let all that water through it. And it's generally not very economic at a small scale.
I came across a company, it's a startup in Canada called Water Rotor, which is a very different technology. I don't know if you've looked at that. It's a horizontal device that sits in a kind of a flume, really, rather than a tube. It's not a screw at all.
No, I've seen one or two things like that. Yeah. In fact, Intermediate Technology Group, ITDG, developed a system for very big livers like the Nile that was just on a boom that hinged out from the side, and the flow of the water pushed it out, and it was just tethered back to the bank. And it was like an upside down vertical axis wind turbine, basically, with and that was sort of successful. It worked fine, but the problem was debris and quite difficult to.
That's it. They talked about vertical axis wind turbines, so you can make a Savonius rotor using 2 cans and slit them. Yeah. Do stuff like that, which is not.
They are good fun, but not very efficient and actually quite dangerous when you've got 2 roughly cut half oil drums spinning round at speed. But we used to have one at CAT, but we got rid of it.
Both the Environment Agency and the anglers would be very again any form of hydro power in the river.
Yeah. Yes, we have enough.
That's the point about this water rotor. They're taking that into account. So it works a bit like a fish race or a fish, whatever you call it, staircase kind of thing. So the fish don't get sucked into the machine at all. I think. I've looked at it a long time ago.
Sounds a bit like what they've
It's still active though, because I just looked at the website.
Yeah. They've got one on the colder, but there's a weir next to it, so I mean the fishermen wouldn't like it at all.
Yeah. I mean, it's quite difficult even here on a little mountain stream in Wales. You need to be really careful with all that. Yeah. And on a big river like the Wye, and one that's so kind of respected, and I think it would be very difficult to get permission.
I'm going to have to go, Bob, because I'm.
Okay, Bob.
Thanks, everyone.
Thank you.
Good.
Good night, Bob.
Right.
It may be time for us all to say good night.
Yeah. Looks like it, yeah.
Thank you, Bob. For those of you who've not yet spoken to Danny, I know has got some appointments booked in, and is contacting everybody else. So nod if you've spoken to Danny or you have an appointment. And if hey, good. Most people are nodding. That's good. Wonderful. Thank you very much, everybody. And I will be in touch soon about the next session.